Hello, everyone. My name is Shachaf. I'm a PhD student at the Hebrew University of Jerusalem. I will present this work. This is a joint work together with the guys, Guy Amir and Guy Katz, and will be presented at ICML 2024. Interpretability talks about the extent to which we can understand the causes of decisions made by ML models. Despite significant advancements in the field of interpretability, many of the existing knowledge is either informal or lacks sufficient mathematical rigor. So here we have some ML researcher which claims that decision trees are more interpretable than neural networks, and another one that agrees and thinks that linear classifiers are also more interpretable than neural networks. And this is, of course, common knowledge in the ML community. However, we would want to be able to formally prove that decision trees and neural network and linear classifiers are indeed less interpretable than neural networks. And previous research suggests on doing this using concepts from computational complexity theory. So the idea is very, very simple. We can analyze the computational complexity of generating different explanations on different ML models. We can then if the explanation can be computed efficiently, then we will regard this model as being interpretable because the model can be explained with ease. However, if generating the explanation is intractable, it's computationally very hard to find this explanation, then we will say that this model is uninterpretable. Let's see an example. So for this type of explanation, it can be found in polynomial time for linear classifiers and decision trees, but it is NP-complete for neural networks. And for this reason, neural networks are regarded as less interpretable under this context because it is harder to find an explanation for them in this particular case. So the explanation form that I just talked about is, as well as many others, is regarded as local. It is an explanation for a specific input X. Let's understand this a bit more thoroughly. So what we mean here is that we have some model F, and we have some input X here, which is the blue image, that was classified to class 1. And this is a specific prediction, and we would want to understand the reason for this prediction, or in other words, why was this blue image classified to class 1? And this is what we mean by a local explanation, because we are explaining this specific image, this specific blue image, the prediction of this specific blue image. Let's see an example for such an explanation. So this is called a sufficient reason, a local explanation, a local sufficient reason. And it is defined in this way. So it is a subset of features. So the subset that you see here, these blue features are the sufficient reason. And if we fix these features to their values, no matter what happens in the complementary of these features, the classification remains the same. It remains class 1. These features are written in free because they are free to take in on any possible value. As you can see here, no matter what we put in the complementary of these features, the classification always remains class 1. And this generally tells us that these blue features are important. Of course, the smaller the subset, the better the explanation, right? Because it contains less information. And specifically, we would be interested in finding minimum subsets, subsets that have minimal cardinality. Of course, I am highlighting that this is a local explanation because it is an explanation over one specific input, this blue image that we already saw. So previous research talked about the computational complexity of finding local forms of explanations. Of course, interpretability can be either local or global. When I will speak about local and global interpretability, I will talk either about the extent to which we can understand specific local decisions or the extent to which we can understand global behaviors. So either that the property holds for one specific input X or that it holds for all inputs in some given domain. Of course, the relationship between the local or global interpretability of an ML model isn't always entirely clear. For instance, in Molnar's book about interpretability, they claim that the weights of a linear model can be used in order to interpret the local decisions of the model, but it is more complicated to use them in order to understand global behaviors. So again, we have some folklore claim, and we would want to be able to formally prove that indeed linear models are more complicated to understand globally than they are to understand locally. So in this particular work, we look at different forms of explanation, and for each one of these explanations, we evaluate the computational complexity of generating either the local form of this explanation, which is over a specific input x, versus the computational complexity of generating the global variant of this explanation, which holds for any x in this domain. Let's see an example. So we again have the previous notation of the local sufficient reason, and this is again a subset of features which is sufficient to determine a prediction. And for the global case, this would look something like that, like this. So we have that this holds for all x, which is what I said before regarding the global variance. And you can see that this is a global sufficient reason because it is sufficient to determine any possible prediction. If we fix the features to these blue values here, then the classification remains class 1 regardless of the free features. If we fix them to these red features, the classification remains class 2 regardless of these free features. And if we fix them to these green features, the classification remains class 3 regardless of these free features. So generally, this subset here is a global sufficient reason, and since it is sufficient for any possible input in the domain. So again, back to the question that I raised before, can we indeed prove that linear models are more complicated to explain globally than locally? And as we show here, we indeed show that for this explanation form, it is harder to explain linear models on a global scale rather than on a local scale. The computational complexity here is higher. And this happens because in the local case, we can use the contribution of each one of the features to develop efficient algorithms, but we can't do this for the global case. And this exactly aligns with the intuition that Molnar et al. Raised for the local interpretability of these models, as opposed to the global interpretability. Interestingly, when we evaluate these explanation forms on neural networks and decision trees, we show that actually the opposite holds, meaning that the local form of the explanation is actually harder than the global variant, as you can see here. This may seem surprising because one would assume that the global form of explanation will always be harder than the local form, but here we show that the opposite holds. Let's try and understand why does this exactly happen. So before I explain this, I need some short notation that will be useful. And I will use this notation of a subset minimal sufficient reason. And a subset minimal sufficient reason is simply a subset of features, which is sufficient. It is sufficient reason. And if we remove any one of the features from this subset, it becomes not sufficient, meaning that all of these subsets here are not sufficient. Of course, a subset minimal sufficient reason isn't necessarily minimum sufficient reason. This subset isn't necessarily with the smallest possible cardinality. These are often referred to as locally minimal or globally minimal. This is the more common terms used for these subsets, but I will use either minimum or subset minimal because we are using local and global under a different context, and I don't want to cause a confusion. Okay, so this is important because we prove in the paper that there can be an exponential number of potential subset minimal local sufficient reasons. As you can see here, these low subset minimal subsets, there can be many different ones, and in the worst case, there can be an exponential number of such subsets. However, in the global scenario, we prove that there is exactly one unique subset minimal explanation. And this is important because this is actually the key to showing that the global task is easier to compute than the local task in many cases. Because in the local case, we have an exponential number of candidates to choose from, and in the global case, we have only one potential candidate. So this is what makes the global task actually simpler than the local one for neural networks and decision trees. But for linear models, this doesn't happen because we have this cheat. We have the weights of the linear classifier that can be used to develop efficient algorithms. And this happens in the local case and not in the global case. And this is what causes the different behavior between the models. So here I mainly discussed the comparison of local and global for the minimum sufficient reason explanation form. But we do this local-global comparison for other forms as well. We compare the complexity of identifying local or global redundant features, local or global necessary features, as well as a probabilistic notion of sufficiency, again, either local or global. So, for example, for the feature redundancy case, we show that identifying, for this definition of feature redundancy, we show that identifying local features that are locally redundant is computationally harder than the global case. So this is for decision trees and neural networks, and this is a similar behavior to before. And this is interesting because it shows us that for this particular definition, it is harder to identify whether a feature doesn't contribute to one specific input, rather than finding that it is redundant for all inputs in the domain. So to conclude, we show that for different explanation forms, there is often a complexity gap between the local interpretation and the global interpretation. We show that this gap can sometimes prove some folklore claims. For example, the fact that linear models can be harder to explain globally than locally in some particular cases. And sometimes we find that these complexity gaps show us some unexpected outcomes. For instance, we show that in many cases, neural networks and decision trees are actually easier to interpret globally than locally, which is a bit unintuitive. Thank you for listening, and